That's the other way to look at the data, of course, is in the percent change in wet weight of the rupia over, it's only a 6-day experiment, and you can see that the small tilapia and the procedural controls and the other no fish control, no significant difference, and there's a loss of the rupia when you have the large tilapia, and they're actually grazing on it as well. And we've also observed that in systems where they put a tilapia in there and they'll just eat all the rupia up. And they eat everything. They eat the roots, the leaves, everything. They leave nothing behind, whereas the water birds, when they consume the rupia here, they'll consume it up to a certain depth, but they're more of a diving bird, so they'll graze it to the point where they can stick their head in the water and their butt up, and they'll graze it all, but they'll leave at least a fringe of rupia in the shallower water so that the rupia can grow back once the birds fly on and use a different wetland. With the tilapia, the point is that they take it all, everything, and they keep hitting at it and hitting at it and hitting at it until it's gone. So I do think that one of the things that we have to look at with these coastal wetlands is controlling for tilapia. Then once you get out into these other coastal wetlands and you look, this is over from Kauai, there's other tilapia that have been released into the system, tilapia zilii and this Oreochromis, which not really sure what, this is the tilapia, this is the Oreochromis. They're all the same tilapia fishes. They've been separated out into different genera, at least for now. But at least these are the other two culprits that we're working with right now with the DAR folks over on Kauai, and we also think that these are having a negative impact on the rupia over in Kauai. The black chin that I don't think it's over in Kauai yet, that was actually an unfortunate escape from the old Honolulu bait station, which is the Sand Island facility. Don't think they've made it to Kauai, but these were intentionally released for aquatic weed control. And we'll keep going with that research as well. And then I'm almost done, but I just wanted to go through the other work that I've been working on out in Mauna Loa Bay. We've run this experiment for about 3 1/3 years and was really interested in the border conflict, if you will, between these two entities, the seagrass and this introduced alga here, and this is what we're looking at. Some of the caveats I do want to mention is I'm talking about a system where there really aren't, it's in Mauna Loa Bay where I don't think there's not excessive other stressors that are land-based. So not chronic pollution, not chronic eutrophication or chronic sedimentation. So sometimes those can give an edge to an invasive species, so it's important to look at that. And the same thing in the Mediterranean. When they've looked at systems in the Mediterranean where this caulerpa growth isn't being driven by strong bits of eutrophication, they get a little bit clearer result. So it's the mixed results that you'll see in the literature showing that the slow-growing seagrass versus a fast-growing alga, a lot of times if they run the experiment long enough, the seagrass, Posidonia, will come out ahead of the alga. Now, that's not true if you have eutrophication, so, which you expect, right? So that's what we're looking at here. So our Hawaiian alternative, and where we're sort of stepping into this worldwide question of what about seagrasses versus invasive species, we're stepping in here and saying, well, we know we have a fast growth seagrass, and at the time we started the experiment, an unknown growth alga. And so we were looking at, well, what's going to happen here if we do this? And in this slide, I know some people have seen it a lot, but it keeps adding, the data keep going on with it, but I just want to talk about, this is the seagrass where I've removed the alga, and that's the alga where it's been removed in the same plot. So we're just going to focus on those, and that's just through time. We started this experiment in June 2004. So you can see that the seagrass and the alga were about the same in these plots. There was some overlap. Looking at percent cover here. We removed the alga, the seagrass came in, took over in those areas within 120 days, and then remarkably for the next 3 years it's kind of held on to its position. And you see here the alga came back to about 20% and just kind of lingers in that 20%, 25% area right there. At this point I want to suggest that that's actually an experimental bias that I had in the experiment. I cleared these sites out so that on each one of the plots, the alga would be bordering at 2 sides of the clearing, and the seagrass would be in the plot as well. It would give the alga an opportunity to enter it back into that plot, or even go beyond the plot through rhizomal extension, which is one way this alga grows. So what you're looking at here is just edge effect. So it's coming in off the sides, and it hasn't really grown that much in 3 years. So when you look at this as a management perspective, you probably want to say this is a good invasive species to look at in terms of removal, because the seagrass is actually very competitive against this alga. So that's what we're going to recommend. And then these are just the plots where we have the alga and the seagrass together, We didn't manipulate it at all, and over time you can see that there's been no, if anything, the alga's faring a little bit more poorly in those plots than the seagrass is, but the seagrass is actually pretty competitive in there. So what we're sort of suggesting is, yep, temporal scale is important, but I think the seagrasses are fairly good competitors against the alga, especially that alga's attached. And I think that this work we're adding a lot to understanding a little bit about how seagrasses respond to the stress of invasive species, at least an invasive alga that's attached. And that's where we're going with this. So, and that's really it.